Hey, welcome back to Calculus. In this video lecture, we're going to start our work in Chapter 5, motivating the topic of Chapter 5, the definite integral, with a couple of problems. One's about area and one's about distance. So you got the learning objectives there. I want to tell you what the area problem is and give you a couple of ways to approximate solutions to it. Among them, these left and right endpoint methods, also a midpoint method I'll throw in there. And then I want to tell you about the distance problem and give you a way to approximate solutions to it using same kind of methods. Okay, so just sort of like what we did at the beginning of the course, motivating differential calculus with those tangent and velocity problems, we're now turning our attention towards this other sort of side of the coin, the so-called integral calculus. We'll see what that means as we work through Chapter 5, and I want to motivate the integral calculus with these area and distance problems. Okay. So what is this area problem? Let's start by talking about that. So on the picture on the right-hand side there, you can see a graph of some function. It's a continuous function, and it's defined on some closed interval from A to B. Okay, so its endpoints are in there. Those are my ingredients that I need. And this function also can't have any negative y coordinates. So something like what's drawn in figure 1 there. Okay, so I've got a continuous non-negative function on a closed interval. And the area problem is, well, and such a function, let me just say, encloses a region, S, that's bounded by, well, the graph of that function, bounded by in the sense that it's the edges. So it's bounded by the graph of the function. It's one of the edges. It's curvy. And then three lines, the line x equals a, the line x equals b, and the line y equals 0. Okay, so those four things together includes this region S, right? And the area problem is find its exact area. And you might think an area problem is a problem out of geometry, right? Why aren't we using geometry? Well, geometry can't really handle regions unless all of their sides are straight lines, or if they're curved, they need to kind of be arcs of circles. Right, so it's this side of the region that is preventing geometry from having anything to say directly about this problem, because geometry just can't handle some arbitrary curve. There's no formulas for areas and arbitrary curves in geometry, right? So it was one of the achievements of calculus to help solve this problem. Now we can work on shapes with more complicated curves. You can think of interesting examples of that. This notation down here in the bottom of the figure, I should say something about it if it's in my slide. It's just a precise mathematical description of the region S. So if you read this out loud, it's saying that S is equal to the set of points x, y in the plane, where x is a number between a and b, and y is a number between 0 and f of x. Right? So for every x between a and b, y can go from 0 up to a point, and that point depends on x. Right? That y can't go as high as this one because the x's are different. Cool. Okay, so how are we going to solve this area problem? Let's look at it in an explicit example. Sort of start us off. Suppose my continuous non-negative function is just 1 over x, and I've picked the interval from 1 to 7. So I'm going to start off not by solving the problem, but rather by estimating a solution to it. Okay? Going to estimate a solution to it. Here's what I'm going to do. I'm going to take my interval from 1 to 7, and I'm going to cut it into 2 equal pieces. Okay, so I'm going to establish some notation in this example as we're going. So that's why I'm labeling this stuff. But I'm taking 2 equal pieces, and I'm going to cut the interval from 1 to 7 into pieces of equal width, 2 of them, and I'm going to call that width delta x. And how do I calculate how wide they are? Well, the whole interval is 7 minus 1, or 6 units long, and I'm cutting it into 2 equal pieces. So I have 6 divided by 2. Each one of my pieces has width 3. So from the left endpoint 1 over here, I'm going to count over 3. It should be right in the middle. It's the number 4. Count 3 more, and you get 7. Okay, so I've taken my interval and I've broken it into 2 equal pieces. Size, length, delta x equal to 3. And now I'm going to select the left-hand endpoints of these 3 intervals. One of them is 1 and one of them is 4. And I'm going to draw a rectangle over the interval whose height is the value of the function at the left-hand endpoint. So I've just finished drawing the first one. And now I've finished drawing the second one. Okay, so the height of this first rectangle, if I just show you on the y-axis, it's 1, and I'm getting it from my function, right? When you tell me an x value, this function tells you the y value. So the height over here at 4 is, can you say it without me? It's 1/4. How tall those rectangles are. And why am I doing that? Well, because in geometry, I do know how to find the area of a rectangle, right? So this is kind of a bad estimate. And again, the notation will make more sense as we go, but I'm going to call it L2. L is for left, if you're curious. I picked the heights on the left-hand endpoints. And the 2 is because I'm doing it with 2 rectangles. But since the area of a rectangle is its height times its width, I can just take L2 to be the area of this first rectangle. Its height is 1, its width is 3, right? So I'll say that that's 1 times 3, and then add to it the other rectangle as area. Its height is 1/4, its width is also 3, right? So I have to take height 1/4 times width is 3. The area of a rectangle is its height times its width. And if you add those things together, you get 3 plus 3/4. Let's just write it as a decimal. It's 3.75. All right, 3.75. The actual area that I'm looking for, the area under the curve, I think certainly looks like it's less than 3.75. Right? That's definitely going to be an upper bound on our estimate, because these rectangles, look, they have all this area that we sort of don't want to count, right? That area that's sticking out beyond the region under the functions graph is area that we've counted in our L2, but we don't want to count it when we're just trying to find the area under the curve, right? So that's why I know that's an overestimate. Good. All right. So another idea to get kind of an underestimate, if you like, is instead of using the left endpoints as the heights, we could pick the right ones. So if I look at this first subinterval, its right endpoint is 4. And so I might draw the rectangle to have height at the right endpoint. The right endpoint over here is 7. So its height would be, can you say it? 1/7. Not worrying about drawing that to scale. So if I wanted to make a so-called right endpoint estimate, then I'm going to use the red rectangles areas. Yeah, that first red rectangle, it has height 1/4, and its width is 3. And the second one has height 1/7, and its width is 3. Right? So we end up having to add 3/4 plus 3/7. And I thought that I had this number written down, but I have to look for it. Sorry, this is kind of awkward. We can write it as a fraction real quick if we want, but let's just write it as a decimal. Sorry about this. It's about 1.17 is what I'm going to write. Sorry about that. 1.17. Took me a second to find it. You can check that on your own. And that 1.17, I already said it, but let me write it down here. That's certainly an underestimate, right? Because there's all kinds of area that's outside of the red rectangles that is under our curve. Okay, good. So pretty crummy estimates. I know that the actual area under the graph of 1 over x between 1 and 7 is somewhere between 1.17 and 3.75, but that's a pretty big gap. So what could we do to improve our estimate? You probably already kind of have the idea. We could pick a bigger number for n, yeah? If we choose a bigger number for n, what's that going to do? Well, on the downside, it's going to create more work because we're going to have more arithmetic to do. But the upside of picking a bigger value for n is that we're going to have skinnier rectangles that fit better. So our estimate's going to get a little bit better. Like let's take here, let's increase the value of n. What if we increased it all the way to n equals 6? What if we increased it all the way to n equals 6? I could kind of start to draw in this picture. You know, I can do the math I need to do. Or this time our width of our rectangles, our step size, sometimes I might call it, it's still 7 minus 1, but this time I'm going to divide by 6 because I'm using 6 equally spaced rectangles. So that they're each width's 1. So in this picture, I'd have to draw in marks for the numbers 2 and 3 and 5 and 6. And then say if we were going to make a left-hand estimate, maybe I could start to draw it. It won't be looking very good if I draw it by hand, but on each one of those 6 subintervals, I'm going to take the height of a rectangle to be the function's value at its left endpoint. Yeah. And in so doing, for this function anyway, I'm on the 4th one, I'm going to get an overestimate of the area. And I think even in my hand-drawn picture, you can kind of see there that that estimate is going to be better than our L2. Yeah, because there's still some stuff sticking out, but it looks like it's smaller. That's what I mean by they fit better. If I were going to draw in the 6 rectangles for the right hand, well, I just have to draw red rectangles whose heights everywhere are at the right endpoints. So in each subinterval, I think I go right. So sort of a crummy hand-drawn picture, but then that would be a way to calculate our R6. What would we have to do to actually start calculating them? Let's sort of think about what the calculation would look like. Say for L6, it's drawn nicer. L6, in each case, we're going to have to think width times height, right? So starting with the left-hand endpoints, I'm going to write it in the function notation, actually. I'd have to take f of 1 and multiply that by delta x. That's the area of the first rectangle. And then I'd have to take f of 2, the next left endpoint, and multiply that by delta x, and so on. Yeah, I'd have to go all the way down to f of the last left endpoint is 6 times delta x. So if we use our summation notation, I could have written that in a shorter hand. I could write, well, it's sum I goes from 1 to 6 of f of I times delta x. And delta x is a constant, so you can factor it out of that sum. You can really read this formula as add up the function values and then multiply that by delta x. So if you really wanted to compute this number, you'd have to do something like take 1 plus a half plus a third and so on up to a sixth. When you're all done with that, multiply it by the width delta x 3 and you'll get your L of x, L6. Okay, I'm not going to do all that arithmetic in the video here. Let's scroll down. I've got a nicer picture for us to look at, and I've already done the computation. All right, so in this picture, you can see my computer-generated image where I've got 6 rectangles drawn. You know their width, it's delta x. We calculated it above, it's equal to 1. And I'm showing you here the function notation, f of 1. Here, each one of these things above, sorry, I misspoke, above, sorry. I don't want to edit this video, I should go back. But up here where I wrote a 3, you already caught this. When you were watching it, you were like, what is he talking about? That's not supposed to be a 3. Delta x in this calculation down here is 1. The width of the rectangles are 1, when n is 6, pardon me. Okay, back to our current here. So I've got the left hand L6 written out there and the right hand. And again, we know that L is overestimating, R is underestimating for this function. So the actual area is somewhere in between those numbers. And those numbers are closer together. And yeah, that's the idea. Here, I've got a picture drawn. I won't even write out the terms in the sum, but here I've drawn the picture with 32 rectangles. Okay, so I took my interval of width 7 minus 1, 6, and I divided it into 32 pieces. So they each have width 3/16. Okay, and for each one of those, for the 32 rectangles, if I picked the left-hand endpoint, plugged it into the function and added all those values together and multiplied it by 3/16, my delta x, it turns out to be a little bit more than 2. Doing it with the right endpoints, it's a little bit less than 2. Those numbers are getting better. Okay, I haven't said this yet, and I'm going to leave it to you in your homework to check it out, but what this M stands for is midpoint. All right, so instead of using the left-hand endpoints to plug into my function or the right-hand endpoints, in each one of those subintervals, you could calculate the midpoint. If you use the midpoint, let's go back up to the picture where the rectangles aren't so thin. If you use the midpoint, it's going to be a nice color to draw this in. Say on this first rectangle, the function's value is there, then you sort of overestimate and underestimate, at least again for this function. So I'm just going to draw a couple of these things, but these green ones would indicate the midpoint sum, if you like, for estimating these areas. So for this n equals 32, the midpoint is about 1.99944. All right. I took some time on a spreadsheet and calculated these things. I didn't do this by hand, of course, but I did it for these. Some of this table, I'm just reproducing what we did above by hand. We calculated this by hand. I didn't calculate it, but it was included above. When n was 6, we had those left and right hand sums. These are approximations for the area under the curve, right? I hope that's what you're processing. 32, we just talked about. It's written above there still. You can still see it. And then I did it for big values of n. A computer doesn't care how big the biggest I went up to was 100,000. And check it out, to 100 at 100,000 rectangles, that left and right hand sum, they're basically about the same, right? That's a 3 decimal places anyway, three digits past the decimal point. Cool. So this kind of motivates the following mathematical definition. I'm going to just define the area under a curve to be the limit of that expression. It's kind of a deep fact, and we certainly won't prove it here in this course. But how I choose my so-called sample points to plug into the function to get my heights of my rectangles, it doesn't matter if f is continuous on this interval. This limit, this sort of complicated looking limit, is going to exist and have the same value regardless of how you pick those sample points. So the author here has written this in using the right-hand endpoints. So in each subinterval, the right-hand endpoint of the first one is x1, the second one is x2, and so on. So he's plugging in right-hand endpoints. His delta x, like us, is b minus a over n, equal width subintervals. N is the number of rectangles. It's the number of terms in this sum. And then for these various sample points, we kind of had given some names above. Ln, the left-hand approximation that we were writing above, the sample points in the book, the author denotes them by choosing it. They're called xi star, okay? And so the xi indicates that it comes from the ith subinterval. So the first sample point, x1 star, has to come from the first subinterval. And then the second sample point, x2 star, has to come from the second subinterval, and so on, right? And if you choose xi star to be the left-hand endpoint, well, then that's how you get your left-hand sum. If you choose xi star to be the right-hand endpoint, okay, that's how you get a right-hand sum. If you choose it to be the midpoint, right, the midpoint of two numbers is just their average, then you get that midpoint sum. In general, we'll tend to use this right-hand sum because, again, there's a theorem that we won't prove that says it doesn't matter how you choose them. As long as you make sure that the ith sample point comes from the ith subinterval, when you take the limit as n goes to infinity, if f is continuous on this interval, you're always going to get the same number. So why not just, let's use this one. In sigma notation, this sum that we're talking about would be written like this. You have one term for each interval. So you let I go from 1 to n. You take the height of the rectangle, f of xi star, plug in your sample point, times the width. That's your b minus a over n. Yeah, so that's a Riemann sum. And again, you can read this formula like this because the delta x is constant. So you can add up the f of xi stars and then multiply by delta x once. Computationally, it tends to make it a little bit easier. This sum's called a Riemann sum after George Riemann, who developed this and many other important areas of mathematics, but was the first to sort of codify this way of thinking about this object that we're leading up to discussing in this class. Okay. I want to say that despite my examples above, ln doesn't always overestimate something, and rn doesn't always underestimate. It depends on the shape of the curve. I'm not going to say too much about this because I want you to think about it in one of your reflections. But our curve above had a certain property that was guaranteeing that the left-hand endpoints always stuck out too far and the right-hand endpoints were short. But you can see in the example that I'm looking at here, it's the sine function. It's the sine function over the interval from 0 to pi. I drew it with 10 rectangles. But L10, some of those left-hand rectangles, look, the first left-hand rectangle's height is 0. It's a rectangle with no area. So they're underestimating for a while, right? But then as soon as the sine function starts dropping, then they started overestimating, and kind of vice versa for R10. But just beware that you can't always say that the left-hand sum is an over or underestimate. It depends on the shape of the curve. And your reflection is going to ask you to kind of dig a little deeper and explain what I mean by that. Okay, this video is pretty long. We're getting there. It's time to, that's what I will say right now about the area problem. The area problem leads to this notion of taking limits of Riemann sums. Let's think about the distance problem. I'll just introduce it with an example. So you're looking at the example. We've got a car. Our odometer is broken. The odometer, you know, is the device that measures the distance traveled by the car. So the odometer is broken in this car, but we want to know how far we go over a 30-second time interval, because everybody always thinks about stuff like that. So not the driver, but someone who can see the speedometer and has a stopwatch records our velocity in miles per hour every 5 seconds for 30 seconds. So that's what the first table is, yeah? So the stopwatch is at 0 and starts. We're going 17 miles an hour. 5 seconds later, 21, 5 seconds after that, 24, and so on. All right. And the question is, well, how far did the car go in this 30 seconds? So how far do we travel? What's our distance traveled in this 30 seconds? So what do we have? We have a function that's giving us our rate, or at least samples of that function. We don't have the function, but we've got samples. We've got this table, our rate in miles per hour, and we want to know how far we went in 30 seconds. Because we don't really want to work in units of like miles per second. We need to kind of stabilize the units here. So let's convert our miles per hour to feet per second, right? Because we're measuring time in seconds. So let's work in feet per second. It'll be more reasonable size numbers than miles per hour. So as the author says, you convert this by a certain multiplication factor. So we're going to use the second table. Okay, so I've gone ahead and labeled here. You can see the time values. Just to have an index scheme, I'm going to call it time 0, t0 up to t6. And I want to know how far I went in this 30 seconds. Well, the principle is that, you know, since distance is equal to rate times time, if I'm thinking of this table as just samples of a function, of a velocity function in feet per second, if I take the velocity, that's my rate, and I multiply it by the time change, so I just assume that the velocity is constant on each subinterval, then I can approximate the distance I would move on that subinterval. Yeah. So this v ti star times delta t, this is the distance traveled on the ith subinterval of time. So if I wanted to say use at each interval of time the velocity at the first moment in that interval, that is, I wanted to make a left-hand estimate, you know what I mean? So from the interval from 0 to 5, I would say, well, the velocity was what it is at 0, the left-hand endpoint. And then from 5 to 10, I would go, well, let's use the velocity of what it was at 5, the left-hand endpoint. So I've written that out here. And again, using the distributive law, I need to multiply all those by the change in t. The change in t here is 5 seconds. That's how often our data was recorded. Right? So you can work that out, and it's 1,130 feet. Similarly, if you take the right-hand endpoints, what does that mean? Instead of using the speed at the beginning of the subinterval, I use it at the end. So over the first time interval, I would use the 31. Over the second one, the 35, and so on. So the last one I would use is 41. That's a little bit longer. It's 1,210 feet. Cool. Okay. Well, this video is getting a little bit long. I just want to say, maybe I can kind of leave that in view just a second as I sort of pan slowly, but these area and distance problems, they both led us to considering expressions that looked like this, where we had some function, non-negative function in the area problem, a velocity function in the distance problem, and we just took samples of it. So we plugged in a finite number of numbers, multiplying it by these sort of widths, thinking of this in the area problem as length times width is area. In the velocity problem, it was rate times time is distance. But in both cases, these sums gave us an approximation for some quantity that we wanted to study. And what our kind of topic of chapter 5 is going to be is that taking the limit as n goes to infinity, n here is the number of terms. If we take n to infinity, then we get the exact solution to the problem. So like area and distance traveled and many, many, many others. All right. So that's sort of why chapter 5 is beginning with this area and distance, because they both are very natural and I think beautiful motivations for our topic of study, which is going to be limits of these Riemann sums. Okay, so I hope you're still hanging in there, and thanks for listening.